Hey there, in this video, I'm going to walk through part of the regression moderation activity for you. I'm going to start here with number 3, the categorical by continuous interaction. We're going to work through this together. For this activity, we're going to use a sample of data from the high school and beyond survey. This is a survey that's sponsored by the National Center for Educational Statistics. These are the same data that we used in the missing data activity, the hsb2.sav file. And you can see that it contains both demographic information and standardized test scores for 200 high school students. So in the first one, I want you to download the data from Canvas, open the SPSS file, and just run frequencies and statistics on the variables just to sort of familiarize yourself with the data set. So let's go ahead and do that right now. So if you see, here's our syntax starter. We need to open our data set, so you need to find where you have it saved on your hard drive. I'm going to copy where I have it saved on my hard drive. There we go. And so I'm going to close any opens data set, open the, get our new HSB2 file, and run frequencies on all the variables. So you can kind of just familiarize yourself with what's in here. Look, there's no missing data, complete cases on everybody. We have an ID variable. We have a variable indicating students' gender, 1 for female, 0 for male. We have a variable indicating students' race or ethnicity, a variable indicating their socioeconomic status, the type of high school they're attending, whether it's public or private, what type of program they're in school, whether they're in a general track, an academic track, or vocational track. We have scores on an assessment of their reading achievement, reading abilities, writing, math, science, and social studies. So kind of get familiar about what's actually in the data set. So number 3, we want to examine a categorical by continuous interaction. And so we want to regress math on reading, the type of academic program, and their interaction. And here I said, let's let academic prog equal 2 be the reference group. So since academic program was a categorical variable, we're going to have to dummy or indicator code that variable, and we're going to set the group labeled academic as the reference group. We're going to treat prog as the moderator variable and reading scores as the focal predictor. When you're looking at a continuous by categorical interaction, sometimes it's usually just more convenient to think of the continuous variable as the focal predictor and the categorical variable as the moderator, but this isn't necessarily required. You could do it the other way. It just makes kind of probing the interaction a little bit easier. So 3A, how do we operationalize an interaction term for regression analysis? So interaction terms are operationalized through a product term. Basically, all we do is we're multiplying the 2 variables together. So we're going to create a dummy variable, 2 dummy variables for academic programs. This has had 3 levels. And we're going to multiply each one of those dummy variables by the reading variable. So in this case, we're going to have 2 interaction variables. So let's work through this real quick. Let me pull up our syntax here. So first thing we need to do is dummy code the academic program variable, and I kind of started this off for you anyways. Want to recode prog. Let's always we'll run a frequency on just to make sure. So prog 1 is general, 2 is academic, 3 is vocational. So we'll recode 1 into 1, 2 through 3 into 0, copy everything else. This part isn't necessary since we don't have any missing data, but always it's good practice just to keep it in there. And we're going to just label this variable. This was the general education. So academic was prog equals 2, right? Yep, academics prog equals 2. So let's complete this sentence here. 2 equals 1, 3 equals 0, else equals copy into academic. And we're going to do the same thing for vocational, except for we're going to change this to a 0 and this to a 1. And then we should run dummy variables on all of these just to make sure we coded everything correctly. So let's, so there were 45 students in the general track. There's 45 students labeled 1 for gen. 105 in the academic track, 105 in the academic track here, 50 in vocational, 50 in vocational. So our dummy coding worked. That's what we're wanting to see. The next thing we need to do is actually generate or operationalize our interaction terms. And we do this by just multiplying the variables together. So we multiply each one of our categorical variables by, each level of our categorical variable by our continuous variable. So I'm just going to call this one gen read, academic read, and vocational read. We'll compute them. And then to examine the interaction effect with the categorical variable, we're going to use a block entry regression approach. The first thing I'm going to do is I'm going to enter in the main effects in our first block, and then enter the interaction terms in the second block. And then I'm going to ask for those, for the F change and R square change statistics. And we're going to look at then the significance level of that R square change value to determine if our set of interaction terms is statistically significant. And so I've tried to annotate what's going on here. You know, our dependent variable here goes on the /DP line. And then for each block of variables that we're going to have, we have a separate method equals enter line. So we're going to enter in our main effects. Since we asked for academic to be our reference group, we're going to exclude it. Remember, when you include dummy variables in a regression model, it's always 1 minus the number of levels you have, and that other level is in your reference group. So we're going to compare general, those who are in the general track, to the academic track, those who are in the vocational track to the academic track. And then in our second method line, so our second block of variables, we're going to enter in our 2 interaction effects. If we were doing like a continuous by continuous interaction, we could enter it all in 1 line if there was only 1 interaction effect, because the R square change and the t-test for that 1 effect would be the same thing. Since we have 2, we want to see about the set of interaction effects, whether they are statistically significant. So let's run this model. Plot my output here. All right, so then we have our standard regression output. Our model summary, model 1 is our first block of variables. Model 2 is our second block of variables. So we can see that the main effects for for reading score and the type of academic program are explaining around 48-49% of the variability in math scores. And this is a statistically significant proportion of variance explained. Since we're interested in the interaction effect, we're going to really look at this second line, and we're looking at this R squared change. So the addition of the interaction terms explained an additional 1.8% of the variance in math scores. And this increase in variance was statistically significant. That's what this F change statistic is telling us. So what this is saying is that the inclusion of the interaction effects are explaining a significant proportion of variance in our dependent variable. So they're saying that yes, we have a statistically significant interaction effect in this model. So let's look at the rest of the output here. So your summary ANOVA table is just basically your overall F test for each block. Notice this F test for model 1 and F change are the same. For model 2, this would be whether the set of variables in your second block were statistically significant. So this is testing whether this R squared value for block 2 is statistically different than 0. So let's talk about our coefficient estimates. How do we interpret each one of these estimates? I'm going to focus on block 2 when we have an interaction effect. So the constant here would be the model predicted math score when all the other variables are 0. So it'd be somebody who was on academic track and who has a 0 score for reading. So this probably isn't a very substantively interesting coefficient. So how do we interpret then the coefficient, say right here, for the general academic track? So the coefficient estimates become a lot more challenging, I guess, to interpret in the presence of a significant interaction effect. But really what this becomes is what we call like a simple slope. So this coefficient here for general academic track is then the estimated difference between someone who's in the general academic, someone who's in the general track versus someone who is in the academic track when the other variable involved in the interaction reading, in this case, is 0. So when you have an interaction effect, the simple slope then becomes, instead of just the mean difference between the two groups, it's the mean difference between the two groups when the other variable in their interaction is 0. So in this case, it's when someone who has a reading score of 0. Same thing for vocational track here. This then becomes the estimated difference between somebody who's on the vocational track and somebody who's on the somebody's on the academic track for someone who has a reading score of 0. And same thing here for the coefficient for reading is the estimated math score. The estimated math score when reading changes by 1 unit. So if a 1 unit change in reading score corresponds to a 0.63 unit change in math score for someone who's on the academic track. Because remember, an interaction effect here is telling us the impact of one independent variable, the impact of academic program on math scores depends on what your reading score is. You could interpret it the other way. So the impact of reading score on math scores depends on which academic program you're in. So this simple slope here is going to be different for those who are in an academic track, those who are on a general track, and those who are on a vocational track. Right now, this variable, this coefficient represents the simple slope of reading score on math score for someone who is in the academic track. So how do we get the effects, the simple slopes, for then the other two levels of our program variable? Easy. We could just re-estimate the model, changing out our reference group each time, and we would get then the reading score, the coefficient for reading score would then be the simple slope for that other reference group. So we'll look at that here in a second. Let's see if we can answer then our questions that are posed in here for number 3. And how do we operationalize an interaction term? We kind of talked about that. That's with a product term, right? We multiply our two variables together. So how do we determine whether there's a significant interaction effect? Remember, we looked at that significance of the R-squared change value. And then if there is a significant interaction effect, how do we interpret the other coefficients in the model? And so we just talked about that as well too. Remember that the interpretation of the coefficients become interpretations of simple slopes, or sometimes you'll hear them called conditional effects, because it's the conditional effect of your independent variable on your x variable, on your dependent variable, when the other variable involved in the interaction is 0. So when we find a significant interaction effect, our next step, what we're going to next do is just probe or explore kind of the nature of the interaction. And I usually always do this 2 ways. I will start by rewriting the regression equation in terms of the moderator and calculating simple slopes, conditional effects, and then using these equations to graph the interaction. Graphing the interaction is really helpful to visualize the interaction. And I've supplied just some generic graphing syntax for SPSS, and you should just change these highlighted parts. This data part here is where you can set the range of the x-axis. The trans lines, you would add and delete trans lines as you need for the number of the number of levels of your categorical variable that you have. So we had our academic program variable had 3 levels, so we're going to have 3 trans lines, and I'm showing you how to generate these equations in a minute. This is what I mean by number 1. Is I'm going to rewrite the regression equations in terms of the moderator. And then you can add and delete element lines here to correspond to the number of trans lines you have. And this is just to give them a label and a color. You can actually change the color here. I just did blue, red, and yellow as the color of the lines. You could change those, and you can change what they're going to label them as well too. So let's talk about rewriting the regression equations in terms of the moderator. So we get the regression equation from our coefficient estimates here. So remember, the regression equation is the constant plus, it would be, their value on what academic program they're in, so whether they're in the general track or not, times their coefficient estimate, plus the coefficient estimate for vocational programs, plus the coefficient estimate for reading score, plus the interaction effects. So I made this little handout here to show you. Oh, I don't know if this works on my screen or not. So first thing we're going to do is write out the regression equation. I kind of showed what's going on there. So we take basically what we found on our regression equation, and so we have our constant plus the coefficient estimate for general, plus the coefficient estimate for vocational, plus the coefficient estimate for meeting, plus the interaction effect for the general group by rating, plus the interaction effect for the vocational group by rating. So now we're going to solve the regression equation in terms of those who are in the general program. So that's when gen equals 1 and vocational equals 0. So we have just the regression equation. And now we're going to solve for those in the general. So we're basically going to fill out this equation, putting a 1 in for general and a 0 in for vocational. See what I did here? 1 and 0, 1 and 0. Every time we see a gen, we put a 1. Every time we see a vocational, we put a 0. Anytime we multiply by 0, anything multiplied by 0 is 0. So those two terms go away. Our equation is reduced to this form. We can then add similar numbers together. And then we have our equation. So now here's our simple slope equation for those who are in the general academic track. Here's the simple slope for those in the general academic track. So let's do the same thing for vocational. So gen would be 0, vocational would be 1. We take our regression equation, plug in zeros for general, 1 for vocational. See where I did that again. Remember the terms with zeros go away, and we add our constant values together, and now we have then, here's the simple slope for reading, 0.408. We do the same thing for those in the academic track. We can identify those who are in the academic track because they would have a 0 for both general and vocational. So we would take our equation again, and now we're plugging zeros in for both general and vocational. Basically, everything reduces to just our intercept and then the value for our reading variable, which makes sense because remember, this was, again, our simple slope we said for reading. So those are the values that I'm then going to put in for, that I'm going to graph in that equation. So there's the equation for academic. Here's the equation for vocational program. And here's the equation for the reading program. Let me pull up my syntax. And so that's what I put in here for general. I put in what we found, 34.2 plus 0.318. 34.2 plus 0.318 read. And so make sure we just label these the correct. And so I do the same thing for vocational and then the same thing for academic. We can run this syntax and we can just get a visual plot of what the interaction effect looks like. If you remember from ANOVA designs, non-interaction effects are represented by parallel lines. non-parallel lines represent an interaction effect. You can see that these lines are not parallel, and it's sort of showing you the interaction effect. You can see the slope for academic track is steeper. So what this is saying is that a 1 unit increase in reading scores has a greater impact on math scores than somebody who's in a general or a vocational track. And you can see here the slopes of the lines are right here. So you can see that those in the academic track, the impact of reading scores on math is greater for those in academic than it is for general and vocational. You can see the slope for vocational is a little bit greater than the slope for general as well. So the next thing I'm going to do is test the statistical significance of each one of these slopes. We already have the statistical significance of the academic slope because that's what's tested in our main model. So to test our simple slopes, I think that's number 5 here. We're just going to recode the variable and just re-estimate the regression equation. When the moderator is categorical, the easiest thing to do is just switch out the reference group k number of times. So that's what we're going to do right here. I've asked you. So we're going to do. So we're going to create a model with dummies for vocational and academic. So we're going to do VOC, ACA, read, and then let me make sure that's what we named the variables. ACA vote, gen read, ACA read, VOC read. Okay. And we'll do the same thing here. We're going to do general, academic, read, enter in our main effects. Let's enter in our interaction terms. And then let's run this model. We'll go ahead and run both of these. And we'll say we still have a significant interaction effect. This value, this change value shouldn't change between here because it's the same interaction effect, set of interaction effects we're testing. The thing that is going to change, though, is this simple slope here. The simple slope is going to change, and the intercept's going to change because we changed the reference group. But notice that 34.2 plus 0.318 times reading is the simple slope formula that we found for those on the general track. Is this? Yeah. So that's another way you could generate these equations. You can just have the computer do it as well. That there's the simple slope. But now we actually get a statistical significance test on this slope, and we can see that this effect is statistically different than 0. We could do the same thing here. We're looking at the vocational track. Notice the F change value is still the same. Both of these F tests are still the same. The difference is the change in the change in the intercept here, and then the change in the simple slope for reading. Here we have then our simple slope equation then for those in the vocational track was 27.56 plus 0.408 times reading. That's what we should have had here in our formula as well, within rounding, of course. And we can see that, yes, this simple slope is statistically different than 0. So basically what this is saying is that the conditional effect of reading on math scores is 0.4. So for every 1 unit increase in reading corresponds to a 0.4 unit increase in math scores for someone who is in the vocational programs. And that is a statistically significant increase. So we would do the same, we'd interpret this model the same way. A 1 unit increase in reading score corresponds to a 0.32 unit increase in math scores for someone who is on the general academic track. So does that make sense? When we in the presence of interaction effect, all of these coefficients then become simple slopes now. So this isn't on the assignment, but think about this for a second. Does this remind you of anything we talked about in this particular kind of example? Remind you of anything we talked about in Stat 2, particularly analysis of covariance? Pause the video right here, think about it for a minute, and then I'll give you the answer. So what we're doing here, you could think of this model right here as pretty much, very similar to what an analysis of covariance would be. We have a continuous dependent variable. Our independent variable, so our main independent variable of interest was the type of academic program, and our rating score is the covariate. However, in this case, since there is a significant interaction between rating score as the covariate and our main independent variable type of academic program, this would indicate a violation of one of the main assumptions of analysis of covariance, which would be that assumption of homogeneity of regression. And really, all the assumption of homogeneity of regression is saying is that there's not an interaction effect between your independent variable and your covariate, because you want your covariate in order for the adjustments that analysis of covariance is making, that you want the slopes, these line slopes, to be parallel, that the covariate is affecting each group, each level of your independent variable the same. And here, this is an indication of a violation of that assumption, that if we consider reading as our covariate, it's not that the influence of the covariate on each level of the independent variable is different, right? The influence of reading on math achievement is stronger for those in the academic track than it is in the general or vocational track. So that's sort of just a connection between analysis of covariance and regression analysis. All right, let's go back to our assignment. So when the regression model includes covariates not involved in the interaction, how are these treated when we graph the interaction and test a simple slope? So this is a good question. If you read in the Darlington and Hayes books, like their recommended approach is to basically you pick a value to hold the other covariance constant at, and a lot of times the mean, you might pick the mean as the mean of the variable, hold all the covariates at their mean, and then do the same probing and plotting procedures. Yeah, just one thing that's not in here that I do want to show you. I think it's up. Yes. Notice what happens. So this was the first model we ran, where I'd also asked for collinearity diagnostics here, and look at the collinearity diagnostics for all of our variables in the model. Uh, usually including interaction terms in your model will cause issues with multiclinearity. In that case, we can still trust this F change test, the significance of the F change test. But the standard errors for our main effects will typically be inflated. Look how inflated these the standard errors are for our main effects. Our coefficient estimate should be estimated without bias, but these standard errors will be inflated. But our simple effect here seems to be okay in this case. What people will do to sort of reduce the multiclinearity and to make some of these values more interpretable is they will center the variables before calculating the interaction terms. So let's look at that real quick. I think that's in the activity. Yeah, okay, so it's the next thing on here. Okay, good. So what we might do then is just center our continuous variable rating score. And we can do this with an aggregate command. So we're going to aggregate and just add variables. We're going to add the mean of the reading variable to the data set, mean read. And then we're going to create a centered reading variable. That's what I have here, the C underscore read. It's just the reading variable minus the average reading score. So let's just run this and you can kind of see what's happening here. I'm going to execute it here so we can actually look at the data set. So you can see the mean read score. So it's just taking the reading score here. So if we just analyze descriptives, read, see the average is 52.23. That syntax right here, just added that as a variable in the data set. And then my C read is then the difference between reading score 57 minus 52.32. And there's my centered reading score. I centered the continuous variable, and then we're going to create our interaction terms from the centered variable. We can, we'll just run one of these just to show you. So notice in the regression output that the model summary information is all the same. Centering doesn't affect then the R square values. Our F change value here is still the same. The addition of the interaction terms is still explaining an additional 1.8% of the variation. We still have the same ANOVA F statistics here. What does change here are our coefficient estimates. Notice the variance inflation factors are much more reasonable now. And notice our constant has changed. The values for the conditional effects of general and vocational change. Notice that the simple slope for reading didn't change. Because this is still the effect of reading. So 1 unit change in reading score still corresponds to a 0.36 unit increase in math scores for someone who is in the academic track. So the simple slope here doesn't change what we had found. But our constant value, the interpretation of it does change. So this is then the estimated math score for someone who is in the for someone who's in the academic track, right? Someone who's 0 on both of these, who's in the academic track. who has an average reading score, so whose reading score is at the mean. This is where it changed. Before, the constant was for someone who had a reading score that was 0, which probably wasn't substantively interesting. This might be a substantively interesting intercept then to interpret, because this is then the estimated math score for someone who is on the academic track and who has average reading abilities, or who had an average reading score. This effect then is then the difference between those who are on the general track and those who are on the academic track for someone who has average reading ability. So for someone whose reading ability is at the mean, they tend to have math scores that are about 3.5 units higher than those who are on the general track. Same thing here. Those who have average reading scores tend to have, those who have average reading scores and who are in the academic track tend to have math scores about 5 units higher than those who are on the vocational track and have average reading scores. So a lot of times centering your variables makes interpreting some of these coefficients a lot more meaningful. It also has the added bonus of reducing the multilinearity. Notice that it's not a big deal if we're only interested in whether the effect was statistically significant, so the F change and R squared change value aren't affected by the multilinearity. It's really the standard errors of these coefficients that are affected. So it'd be hard to interpret. If we wanted to interpret these coefficients and want to know whether they were statistically significant, we'd probably want to do some adjustments to reduce the multilinearity, because these standard errors would be inflated in that case. All right, let's go back to the assignment. I'm going to let you work number 7 on your own, and we're going to talk a little bit about continuous by continuous interaction. And so we're going to follow the same steps. Here we want to regress math on writing and science and their interaction. And then we're going to center both writing and science, compute their interaction between the centered variables, and rerun the regression model. So I'm going to let you play around with both of those. Those number 7, I'll let you compute those up. So, you know, number 8, continuous by continuous interaction. We want to create an interaction term between writing and science. And then we're going to enter these variables into the regression model. So our dependent variable is math again. We have write. Oops. I need to put an after enter. Right, science, and then. So in this case, I'm going to actually show you this. It's not going to matter. I don't have to really enter them in 2 blocks, since it's only one interaction effect. You can get the results will be the same either way. You can see the what you do get by the addition by running them with the in blocks is you get the R squared change, which you don't get before. But notice the sig f here is 0.007, and same thing with the significance value, the p-value of the interaction term. They're going to be the same. This f change here, when we only have one variable, we could compute it by just t value here. If you square it, 2.72 squared is 7.3 0.3984. So, within rounding to what this F squared change is. So you can get the same thing. What you don't get here, we know that the inclusion of the interaction effect is statistically significant when we included the interaction effect, even without doing it in the block entry way. But the block entry, we get the actual R squared change value. You don't get it when you do it this way. We don't know what the R squared change value is. So even with just one interaction term, the sig value is the same. Either way you enter it, the F change value you can get by squaring the T value here. I still like to do it with the block entry method. So how do we interpret these effects? So this main effect then, so this would be the impact of writing score on math achievement when science scores are 0. Same thing here. This would be the impact of science scores when the impact of science scores on math scores when writing scores are 0. The next thing we want to do is, we might want to probe the interaction. And so it's a little bit more challenging here when we probe an interaction between two continuous variables, because in order to rewrite the regression equation in terms of one variable, we have to just arbitrarily choose values to hold constant at the other variable. When it was categorical, it was easy because we could just pick each category. When we have two continuous variables, we just have to arbitrarily choose which values to pick if we want to be able to rewrite the regression equation in terms of those values and graph the interaction. So a lot of people will choose the mean, maybe one plus or minus one standard deviation of the mean, or choose like the quartiles, 25th, 50th, 75th percentile. But really any meaningful value will do. And on here, I ask you to use the centered equations, and then for science, hold out its mean, as well as 10 points above and below. I think that's the mean plus and minus one standard deviation. And you can follow along in the syntax here for, here's centering the variables, graphing them in order to rewrite. So here's why I rewrote. You can see my values for how I rewrote the equations in terms of science, and then you can see I changed my labels: minus 10 points at the mean, plus 10 points. I do want to talk about a little bit about this Johnson-Newman technique. So rather than just arbitrarily choosing values of one of your continuous variables to hold constant, like the mean plus or minus one standard deviation of the mean, we can use this Johnson-Newman technique, where we basically examine where on the continuum of the moderator variable are the conditional effects of the focal predictor statistically significant. So in our example, we were looking at, we were regressing math on writing and science scores. So we could ask where on the continuum of science scores is the conditional effect of writing on math achievement statistically significant. Now, there are no native ways to do this in SPSS, so we need to use the, you could probably do it by hand by, just calculating different, rewriting the regression equation various ways and calculating simple slopes either each way and testing, getting that t value. But the RLM macro that they describe in our textbook will do this automatically for us. I have, here's a link to it on the Canvas site. So if you haven't downloaded it from the book's website, you can download it here as well. And we're going to use this RLM macro to calculate these various conditional effects, so we can see where on the continuum of science scores is the conditional effect of writing on math achievement statistically significant. Let's pull up our syntax here. So for here, we're going to need to use the RLM macro. So you need to enter your file path for the macro. Let me copy that. There we go. And so, I just saved the macro to this folder on my computer. This is where it's located. And I just use the insert file command to run it. I'm setting print back off and print back on, so then it doesn't print the entire syntax file that's in there, because we don't need to change anything within that syntax file. So I'm just going to set it there on my computer. And then we call the macro with the macro name. We use y equals and give it the dependent variable, /x equals our independent variables. And then the first variable we enter, well, actually, I think they consider what the second to last and last variable. This would be our focal predictor, and the last one's our moderator. This is to say create an interaction term, and this part is to run the Johnson-Neyman technique. In Appendix A in the textbook gives you all the details about this macro, but I'll try to explain it as we use it in this class as well. So we could run the analysis here, and you'll get this this output. We can check our dependent variable is math, our focal predictor is right, and our moderator is science. If that's not what we want to flip these in the syntax to flip which one is the focal and moderator. Here's our sample size. Notice we get the same. We get the same R squared value, the same F test that we got in. So that's our R squared value. There's our F test. This is the same one that we have printed here. Same summary node table. Same regression output statistics. Here's our constant. Here's our interaction. Here we go. There's our constant. There's our interaction value. So you can see that these are all, we get the same results doing it this way. Here's the change in R squared statistics that we got. Here are our, here's the zero order, semi-partial, and partial correlation. This is what SPSS calls the part correlations, if we ask for that. And this right here, this part is the Johnson-Neyman technique. What it's doing here is it's searching for different values of science. So it's basically centering the science value at 26 through running the regression model, and then getting the simple slope for writing here, and running a t-test and seeing whether it's statistically significant. So we're seeing that where on the continuum of writing, where on the continuum of science achievement is the conditional effect of writing statistically significant. And right here, it sort of tells you that at values of science at 36.4573 and higher, the conditional effect of writing on math scores is statistically significant. Notice that when we get to this value, this is where the p-value then flips from non-statistically significant to statistically significant. So we would say, values greater than 36.5, science fair greater than 36.5, the impact of writing on math achievement is statistically significant. And you can see that this is the effect of that variable. So notice that the value here is in the simple slope for writing when science score is 50. And you can notice how each one of these increase. If we go from 1, so if we went from 50 to 51, this would actually increase by this interaction effect by 0.014. So let's see, we're going from 50 here, so we go from, the conditional effect is 0.3783, so 0.3738 plus 0.014 times, let's go to our next whole number here to make it easy, 62, so times 12, and we get around 54. When I multiply this in my calculator, I get 54.5418, 0.5424, so it's pretty close within rounding that bit, because all these numbers are rounded. This, then, you can see that the interaction effect is the incremental increase in changing each unit from the change of the conditional effect when, so this would then be the conditional effect of writing on math achievement when science is 0, and it increases for each 1 unit increase in science. That conditional effect changes by this interaction effect, and you can kind of see that happening here too. So this is saying that basically what we're finding out is that the conditional effect of writing on math achievement is statistically significant when science achievement scores are greater than about 36.5. You can see here when science scores are 0, it's not statistically significant. And then I try to demonstrate something similar here. When you're if you were going to calculate these by hands, we could basically just center science at one of these values. So here I'm just centering science at 35, computing the interaction with writing, and then I get I'll get the conditional effect of writing when science equals 35. Here is my my conditional effect of writing when science is 0. So in this case, 0 is science is at 35. We get 0.163, and look, it's not statistically significant. There's our interaction effect. The value of it didn't change. Let's find one of these. Let's do 47.6, and we're going to read. I'm going to copy this. Minus 47.6. I need 476. I'm going to change that to 2. And here's our notice our conditional effect for writing when science is at 47.6 is 0.34. It is statistically significant. And what do we find here? 47.6.340, and it is statistically significant. So that's really what's going on with the Johnson naming technique is we're trying to find out at which values of our moderator variable is the focal predictor, the conditional effect of the focal predictor statistically significant. So you can work through some of these. I think working through it and practicing interpreting the regression coefficients will help you kind of understand what is going on. Next thing I show you in assignment is the categorical by categorical interaction. You know, this is, we could do the same thing we basically do in an ANOVA type design, because really a regression model with 2 or more categorical variables is an ANOVA model by design. So anything that we did, probing interaction effects in ANOVA designs, we could do the same thing in a regression sense. And then finally, the assignment ends with introducing you to different types of categorical coding schemes. I would highly recommend reading these few pages in the Darlington and Hayes book to really give you a good overview of different coding schemes for categorical variables and when it might be important or substantively interesting to use these different coding schemes. And in the syntax here, walk through some of these with you. So here's how we would do, you know, indicator coding, dummy variable coding. Here's how we would do effect coding, and we can see that the coefficient then represents the difference in the mean of group J, you know, so the mean of whatever that group is compared to the overall mean, and then what the constant of that variable would equal. So you can kind of practice going through that and practice interpreting those coefficients yourself. So hopefully I think this, the rest of the moderation activity is pretty self-explanatory. Like I said, as you're going through it and you have questions, you know, please let me know what questions you have, and I'll try to do my best to answer that or clear up any confusion. Thank you, and I'll see you guys in the next video.